Morning.
Morning, Stat. What are you doing?
I'm here to help you talk about spreadsheets.
You're Stat the cat. You're not Spreadsheet the cat.
Yeah, but it's a statistical spreadsheet.
Yeah, we're going to dissect this. I told the students in class I'd show them how to make some of these graphs.
Can I help?
You can be quiet and sit and watch.
Okay.
So, I told you in class, I'm going to kind of go through how I created this and point out that to some degree, any of you could create this. But we're going to start with some basic graphs first. So, this sheet is on Schoology if you want to play with it. And it's just some basic functions. So I'm going to do the scatter plot, and I'm doing the smooth scatter plot. I had this typo the other day. I'll fix this typo before I put it, there we go, before I put it out on Schoology. You will notice that even though I've only got -2, -1, 0, 1, 2 for my x values, it smooths this out pretty well. You may notice it's a little lumpy on your computer, but it's not bad. And that's just a basic smooth scatter plot. I could do any function I wanted to. But once I realize I can do that with a scatter plot, I can force all kinds of things into it. Instead of this being a parabola, I can turn it into a bowl. I can add, I'll just call it, I'm going to name this line, these two values. I'm using this tab key to get the other lines in here. And now I have a bowl instead of a parabola. I really can do this kind of anywhere I want. I could draw lines all kinds of places. I could do -1, +1, 1, 1, and select data, add, call this line 2, select my x values. I'm using the tab to get here. Notice this little weird brackets around the 1. You want to make that go away. You don't want to add to it. You want it to be gone when you do this. I got two lines, so it's hard to see, but you can change the color to any color you want. Do bright green. So you can put different pieces on the graph. And if I wanted to move things around and do lines differently, I could do a function here. I'm going to change this one just to show you what I'm talking about. Whatever I put in for this x value here, I'll make this my input. I want to put the opposite here, and I'm going to go ahead and use the function here. So now my graph just became interactive. Well, let's see, 0.75. Yeah, wherever I want to put it. So I can move that line wherever I want with a dynamic input. I can put all kinds of functions on here. I can put a different mathematical function on. And get all kinds of interesting things that I might want to get. Um, Notice it was auto scaling, and how much you want to draw is kind of up to you. So this just gives you an idea of the kind of things you can do with the graphing tools. You saw me change colors. You can change the here we go. Where you can change all kinds of things. I'm not going to go through these here, but you can change the thickness of the line. You can have the outline and all kinds of crazy things. You can put the dots back on them if you want to change the style. There's a lot you can do with it. But we want to, of course, figure out how we did this. So Um, we're going to go over to standard normal for a moment. Now, one of the questions that you have to deal with in this situation is how detailed do you want your x values if you're just trying to graph a function? I did integers here, and it doesn't look bad. Over here, instead of integers, well, I do have the integers. And we'll look at what it looks like. On the spreadsheet that we're going to try to mimic, I went by tenths. That was a long time ago when I created it. I think probably 0.5s or 0.25s would be enough. For this demonstration, though, we'll just go with the integers. Now, I threw on here, just to remind us, some normal distribution stuff. That is what the normal distribution function looks like, with a standard deviation of sigma and a mean of mu. Now, where I'm doing the standard normal, which means the standard deviation is 1 and the mean is 0, so it makes it a little less complicated. But I wanted you to see in the spreadsheet what you would have to do if you didn't have the normal function. There is that function implemented in the spreadsheet, again with a mean of 0 and a standard deviation of 1. And here is how I did it. Now this is the first place. Let's go ahead and graph this, and I'll show you why I'm doing it this way. So that's the graph. Insert, and we get the standard normal distribution. Let me get this function out of the way. It's kind of ugly anyhow. And I think this graph does look a little lumpy, so I'm going to go to 0.5s instead of integers. Um, but on this function, this is the first time you see me use false instead of true. Well, what the normal distribution function does, how it works, is the when you use true, it's telling you, I'll go back to this one since this is a normal. True is saying, give me the probability of being from this point all the way to the left, the cumulative probability. That's how these p-values are being calculated. False tells you what is this point on this curve. So this function is this curve. When I do true, it's integrating this function from whatever point I'm at all the way to the left, to negative infinity. So I wanted these to be false because I don't need the probabilities, I just need the curve. And you can see that the norm.s.dist function does work the same as this really ugly formula. Of course, this is the standard normal. And over in this, your null hypothesis and your sample size will change what this distribution is. We did this a little bit in class. If my hypothesis is 0.75 and I've got a sample size of 200, well then my sampling distribution looks like this normal curve. If my null hypothesis is 0.4 and my sample is kind of small, then I have this sampling distribution. So I've got to make what I just did here be interactive for different means and different standard deviations. So let's just slide that out of the way. But I also want to make sure that the graph still goes from 3 or 4 standard deviations below to 3 or 4 standard deviations above, no matter what that standard deviation is. So I'm going to first make this less lumpy. I talked about that. I'm going to insert some spaces here. And I just guessed at how many spaces I need. Oops. So I want to go from -4 to +4. I need to go a little bit further. Now, why am I inserting these? I'm inserting these so I don't have to redo the graph completely. By inserting, when I go back to here to select the data, it does the insert for me. Okay, now I've got -4. This was here, I believe. Oops. We'll get this out of the way because it's not really doing us any good anymore. Notice the curve smoothed out a little bit. It's a much better looking graph, but it's still not interactive. This is still the standard normal. So what if I wanted to do a different mean and standard deviation? Let's just go with 45 and 6 for no particularly good reason. I want to graph that. Well, I still want to graph it from 4 standard deviations below this to 4 standard deviations above this. So I'm going to insert in here my x's, not my z's, the x's for this distribution right here. And 4 standard deviations below the mean, I would take z of -4 times the standard deviation plus the mean. It's a -4, so it's going to go below. And I'm going to want to copy this all the way down, so I have to lock the two references to the mean and the standard deviation. So in this case, 4 standard deviations below the mean is 21. 4 standard deviations above the mean is 69. The mean, 0 standard deviations from the mean is 45. Now this is going to work no matter what goes in here. These just became my inputs. So I could do a different distribution. And I'm going to get 4 standard deviations below to 4 standard deviations above. I'll go back to the 45 and 6 for now. And I no longer want to use the norm.s.dist. I want to use just the norm.dist. Oops, there we go. With this mean, okay, I'm going to lock the reference. This standard deviation, I'm going to lock that reference. Notice it adjusted a little bit, but it's just the wrong data now. So I'm going to take this out. I could fix this one. I think it's easier to just start over. These z's are only here to make sure my x's run from 4 standard deviations below to 4 standard deviations above. And these normal values are now based on this distribution, not the standard normal. So this is my x, this is my y. I'm just going to redo my graph from scratch. So it's centered in the right place, centered at 45, the standard deviation is 6. If I increase standard deviation to 10, it went shorter and wider. If I lower the standard deviation to 2, it gets skinnier and taller. If I do a completely different standard deviation, it completely rescales. That still doesn't quite look like this one, because now I want to get this bar on here. I want to have a particular point that I might want to find. So how would I do that? Well, I could do that a couple of different places. I'll do it up here. Just put my x that I'm looking for. I can call them x and y, I can call it x and whatever. We'll only do one input here, and you'll see why in a second. So let's say it's this distribution, and I'm trying to draw the line at 105. Well, I want to have two x values. Oops. And I want to have two y values. Well, the first one, I'm hard coding 0. I know we talk about not hard coding, but I hard coded my z's, so I'm hard coding this. And now I do the same function I did over here. I'll just retype it. Norm.dist of 105 with this mean this standard deviation. And again, I want false because I don't want a probability, I want a point on a curve. So I'm going to add, let's call it point, these x values paired up with these y values. So now, in this distribution, I can look at different options and see where they land visually. If I want to find the probability of being below that point, now I'm going to use the norm.dis function again, but use it differently. I just won't put that on the graph. So if I want to find the probability, I'll do it this way. The probability of x less than, in this case, 85. Norm.dist, 85. This mean this standard deviation. And now it's true. And that's be about right, 15%. Now I didn't make this one interactive. I can do that. I can make this spot also refer back to this blue input. And now it's just my label that's wrong. So if I change this to 115, I got my probability and I've got my point on the graph. This is starting to get a whole lot closer, you may have realized, to this. It's working the same way. Because over here, my hypothesis determines my mean and my standard deviation. And once I have my mean and standard deviation, I'm just doing what I did here. And then my sample data determines the sample point. And then with that point, I do what I just did here. So I'm going to start unhiding some things here in a moment, but take a bit and see if you can kind of recreate what I've got here first. So let's unhide a few things. Click up here and make the font everywhere the dark black font. And a couple things pop up that were kind of hidden. There is how I get the data for this orange bar. So if my sample had been 80 and there were 45, it computes the p-bar and then it just feeds the p-bar over here, forces the 0, and uses the norm.dist. Now you notice this is an older version, norm.dist instead of norm.dist. It doesn't make much difference. I told you this spreadsheet goes back a ways. And do 35, make it a little more visible. Over here, it's going to be hard to see this because of the few things on top of this. I'm going to grab the chart and slide it out of the way. And this, I mean, over here, you may, so how did I do this? This is just a wide column with things typed in here for the students. This is a text box. If I right mouse click on it, I can move it around. I can do all kinds of crazy things with it. So I'm going to get that out of the way and stick it over here just so that I can do this. Notice I went by tenths. I mentioned that. So I got -4 to +4. I did put the values in here. Now I don't really use column B, but they're here. And notice I didn't use a norm.s. I used the regular norm. You can use a norm.dist, and I hard-coded in the 0, 1 for the standard normal. But the column B isn't really doing anything in this graph. I could literally just clear it out. You know, again, what I had on an older version of this is I had two graphs. I had the sampling distribution and the z distribution, showed how they moved together. That may or may not have been better for educational purposes. But that column really isn't necessary. I'll leave it there for now. And then the p-bars, this is what I did over here. I'm taking my mean and my standard deviation, and I'm going the mean plus -4 standard deviations from the mean. And I do that all the way down to create my x values. So this is equivalent to what I did right here. And then I use, again, the norm dist. I don't have the dot. We need to upgrade this probably next time I teach statistics, which I think is in the fall. I'm probably going to upgrade this to the newer functions. And I just use the same stuff. Now, where did I get the mean and the standard deviation? Well, those had to be computed based on the null hypothesis. If you remember your sampling distribution theory, if I'm taking samples from a binomial distribution, a yes-no distribution, that has a 40% yes or 40% success probabilities, well, the mean is 0.4. If my population is 0.5, the mean's 0.5. Oops. So the center of the sampling distribution changes based on what I've said for my hypothesis. If I say the null hypothesis is 0.75, it's going to be centered at 0.75. 0.4 centered at 0.4, 0.5 centered at 0.5. That's the same kind of interactivity I had in the other one. The difference is this goes through two steps. It goes from this input over to this mean calculation and then goes from that mean into there. Why did I do that over here? Well, part of it's for completion. And then where did I get the standard deviation? Well, this may look a little bit familiar, but the standard deviation of the sampling distribution of p bars is your hypothesized proportion times 1 minus your hypothesized proportion divided by the sample size. And you take the square root of the entire mess. So it's using that. So these two inputs are feeding over into what is the mean and standard deviation of this normal distribution. So that's why if I have a larger sample, the standard deviation goes down and this becomes a taller, skinnier distribution. If I have a smaller sample, the standard deviation goes up and I have a shorter, wider distribution. That's the height of the graphing stuff there. And again, it's kind of hidden in the original. And some of these get a little more complicated because they're slightly different functions. But all of these work on the same, that's a chi-squared test. It's a bad example. There we go. All these work on the same principle. This one's using t-distribution functions instead of z-distribution, instead of normal distribution functions, but it's the same concept. So once you've done that and you get the formulas right, they all work. So what else is going on over here? Well, the p-bar calculation is pretty straightforward. So the observations are the successes divided by the number of observations. And the z-score calculation is the z-score calculation. It's this p-bar minus the mean from over here divided by the standard deviation. And I did actually round. I didn't just round off the display. I really did round off the value. This is just because a lot of textbooks, a lot of statistics textbooks use tables and z-scores are rounded off to 2. So if this spreadsheet is going to give you the same output that the table would give you, I had to round off the output. I couldn't just round off the display. So that's what that's about. But here, we look at it, I'll do it this way. There is the z-score calculation. Then it's wrapped into a rounding function. Then where do these p-values come from? Well, again, I'm rounding to 4 decimal places to match textbooks. The truth is, in the real statistics world, you would not want to do that necessarily. I mean, 4 decimal places is enough, but you don't need to do that. But the actual function, here we are. Norm.s.dist, find the absolute value of my z-score. I'm using the absolute value to make sure I go the correct direction. And I want true. I want cumulative probability. And the one below it, you double it. It sounds kind of silly, but you simply double the result of the one-tailed p-value. You may remember that from your stats classes, that a one-tailed and two-tailed essentially just doubles your p-value. But it's using the norm.dist at the absolute value of the z-score. And the reason I do that way, again, what if this went the other way? So right now my z-score is positive. I'm above 50%. I got a 0.58. What if I went the other way? Well, it's a negative 1.29, but I want to make sure this is looking the right direction. So the p-value would be less than 10%. With the 35, I get the same one because it's assuming that if I get a p-bar above my null hypothesis, it's assuming which direction I'm looking in my alternative. You notice there is no alternative hypothesis on this sheet. I have a version that puts in an alternative, and it has an up or a down, and it changes these formulas, and really just gets more complicated. This makes the output more like what you would get out of SPSS. SPSS would do this p-value based on whichever direction the sample value goes. But that's, that's a dissection of this. Feel free to look at the other ones. You can't screw this up because you can just download it from Schoology again. You can kind of guess looking at the significance test for means, where I've got these very narrow columns. That's where the stuff is hidden. As this has morphed over the years, I think this is the one. I think it's all hidden over here. See if I'm right. Yep, it's hidden over there instead. I think it's cleaner that way, and I just haven't adjusted the other ones. So the output and the input for the students is over on the left-hand side, and then kind of the tricky hidden stuff's over on the right. Where my older versions, I had the tricky hidden stuff over there. You can argue which one's better. This has something called effect size, and that's just some simple formulas out of a textbook. That has really nothing to do with the kind of stuff we are talking about today. Oh, it's also got the chi-squared test. Let's talk about that one too. So I'm going to, again, take a quick break here. You should look over this proportion one until you're kind of comfortable with it, and then we'll come back and look at the chi-squared test. Let's take a quick look at the chi-squared test of independence. I don't want to spend a whole lot of time reviewing what the chi-squared test is, so I found a quick example over on Google, which is a wonderful tool for things like this. So we're just looking for a relationship in a chi-squared test between two categorical variables. So this is data based on marital status. These look like the Census Bureau statuses, and educational level. So I've got to get these. Well, if I do it this way, there, and do that. I got to get these values typed into here. So I've got 18, 36, 21, 9, 6. This is getting boring, so I'm going to pause the video while I fill the rest of these in. Okay, I'm going to fill the last couple in. I want you to watch me do this. I'm going to drag that to a different screen. You have to just trust me that these numbers are correct, because I want you to see what's happening down in these other tables. I've got the first 3 rows completely. Down here, I still have a 9, a 6, and a 3. So 9, 6, 3. The labels are gone. Notice it counts rows and columns automatically. So I can put this in. This chi-squared will go up to a 6 by 6, 6 categories by 6 categories. This particular problem is 4 categories by 5 categories. And the question is simply, is there a relationship between them? If you look at the data, obviously row 4 was widowed. There are far fewer widowed people in my sample. Well, widowed and divorced both have 30. So I would expect this column was high school. If there's less people who are widowed and divorced, I would expect less high school or less widowed and divorced high school graduates. If there are more married people than anything, and there's no relationship between marital status and education, then I would expect every educational status to have more married people than any other group. So this right here is an interesting visible anomaly that in my overall population, my never married is less than 2/3 of my married, but high school graduates, they're equal. So you start thinking, well, maybe there is a relationship. So what chi-square testing does, it takes what I'm going through here kind of verbally and does a calculation. It says if marital status has nothing to do with educational level, then with these totals on the margins, I would expect the individual cells to have these frequencies. So we do see that if there was no relationship between education and marital status, instead of 36 never married and 30 high school graduates and 36 married graduates, I'd expect 27 never married high school graduates and 45 married high school graduates. So you see the numbers don't match exactly. And then the chi-squared question becomes, well, they don't match exactly, but how much don't they match? How different are they? And it goes through a calculation and computes something called a chi-squared statistic, and then you get the p-value. So in this case, this is a fairly small p-value. We would reject independence is the phrase, and we would assume, we conclude that there is a relationship between marital status and educational level. This doesn't tell us what that relationship is, it just tells us that there is one. But the part about the spreadsheet I wanted to show you is, for example, here, when I hadn't typed, I'll just do these two. When I hadn't typed these, notice it didn't do the calculations, anything. How did it know not to do anything? Well, down here, I simply used the isNumber function. So if there's a number up here, then go ahead and do this calculation. And that, by the way, is the expected frequency calculation. You would see that in a book. You'll notice it's a mixed reference. I lock a row, then I lock a column, and then I lock a specific value. So I'm locking row, column, total. So if I go to a different place in here, it's a different row, different column, same total. This is one of those where I was able to use the mixed reference. I put the formula here first and copied it through the entire table. Down here, it's the same idea. It says if there's a number, then you do this component thing I'm not going to get into. But it makes it a very clean chi-squared test. So if I had a very small problem, or a much smaller, won't go tiny. If I had a problem that had 3 and 3, it just leaves those blanks. And then go down, of course, I can go down to a 2 and 2 if I want to, or a 2 by 3. It's kind of up to you, but that's kind of a neat one of choice of that isNumber function that basically says don't do anything if it's not a number, or just leave it blank. If it is a number, hey, do this calculation. That's another piece of this template that's worth looking at.